November 3, 1943, 32,000 feet above Wilhelmshaven, Germany. Staff Sergeant Thomas Callahan's hands moved smoothly across the control handles of his Sperry ball turret, tracking a Messerschmitt Bf 109 that had just broken from a formation of German fighters diving on the bomber stream below. The fighter was closing at over 400 miles per hour in a climbing beam attack, coming up from the bomber's 4 o'clock position at an angle that would bring it across Callahan's field of fire in perhaps 3 seconds. His feet adjusted the range dial, framing the Messerschmitt's wingspan between the reticule lines of his K4 computing site. The turret rotated smoothly, swinging him and his twin 50-caliber Browning machine guns through a 90-degree arc in under 2 seconds, the hydraulic system responding to inputs from the site's analog computer with a precision that seemed impossible for 1943 technology. The reticules shifted automatically, calculating lead angle based on the turret's rotation speed, the range he'd set. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. And ballistic data built into the mechanical brain hanging above his head. He pressed the firing buttons atop his control handles. Both guns hammered, sending a stream of 50-caliber rounds into the space where the Messerschmitt would be in half a second. The fighter flew directly into the cone of fire. Cannon shells from its wings flashed past Callahan's turret as the German pilot's last burst went wide. Then the 109 rolled inverted, trailing smoke, and fell away toward the cloud deck below. What Callahan couldn't know as he searched the sky for the next threat, was that the system allowing him to track and hit a target moving at combined closure speeds exceeding 600 miles per hour represented one of the most sophisticated hydraulic control systems ever designed for aircraft use. A system that engineers at Sperry Gyroscope Corporation's plant in Lake Success, Long Island had told the Army Air Forces couldn't be built. Not with the weight restrictions, not with the power limitations, and certainly not with the precision required to track targets that fast. The man who proved them wrong had never graduated from engineering school. He'd dropped out after 2 years to take a job during the Depression, but what Preston Tucker lacked in formal credentials, he made up for in an understanding of fluid dynamics that would revolutionize bomber defensive systems and save thousands of American airmen from German fighters over Europe. This is the story of how one engineer's impossible hydraulic system made B-17 turrets track targets at 400 miles per hour. The problem facing American bomber designers in 1939 was brutally simple. German fighters could approach at speeds exceeding 350 miles per hour. American bombers cruised at around 180. That meant combined closure rates of 500 miles per hour or more during beam attacks, where fighters came in from the side. A gunner trying to hit such a target had to lead it by dozens of feet, calculating deflection angles while the target crossed his field of view in seconds. Manual gun mounts, where the gunner physically moved the gun by hand, couldn't traverse fast enough. By the time a gunner swung his weapon to track a crossing target, the fighter had already passed through his cone of fire and was either breaking away or pressing the attack from a different angle. The math was unforgiving. A Messerschmitt 109, approaching at 350 miles per hour from a 90-degree beam angle, covered 514 feet per second. At typical engagement ranges of 600 yards, that gave the gunner approximately 3.5 seconds from first detection to the moment the fighter flashed past and escaped the gun's field of fire. But human reaction time consumed nearly half that window. The gunner needed time to spot the target, assess its trajectory, begin tracking, estimate lead, and open fire. By the time these sequential processes completed, perhaps 1.5 seconds remained for actual shooting. Against a crossing target requiring significant lead angle, manual gun mounts simply couldn't traverse fast enough for the gunner to establish proper aim and deliver effective fire. The British had recognized this problem early. Their Boulton-Paul turrets, developed in the mid-1930s, used hydraulic power to rotate gun positions at speeds manual operation couldn't match. A gunner operating a Boulton-Paul turret could swing his weapons through 180 degrees in just a few seconds, maintaining smooth tracking throughout the traverse. American observers at Wright Field in Ohio studied British turret designs with great interest in 1939 and 40. The British approach worked, but it carried significant weight penalties. A Boulton-Paul turret installation, including the turret structure, hydraulic pump, fluid reservoir, control valves, and associated plumbing, added over 800 pounds to an aircraft. For a heavy bomber like the British Lancaster with 4 powerful Merlin engines and considerable payload capacity, this weight proved acceptable. For American bombers being designed to more stringent weight budgets, 800 pounds per turret installation threatened to compromise range and bomb load beyond acceptable limits. The Army Air Corps issued specifications for powered turret systems in early 1940. The requirements seemed contradictory. Turrets must rotate at speeds sufficient to track crossing targets at closure rates exceeding 500 miles per hour. Total system weight, including all components, must not exceed 450 pounds for upper turret installations or 600 pounds for the more complex ball turret system. Precision must allow gunners to maintain smooth tracking throughout high-speed maneuvers. And critically, the system must operate reliably at altitudes above 30,000 feet, where temperatures dropped to 40 below zero and air pressure fell to less than 1/3 sea level values. Sperry Gyroscope Corporation received the contract to develop turret systems for the B-17 Flying Fortress in May 1940. Sperry had built its reputation on precision instruments. Their bomb sights gave American bombardiers the ability to hit targets from 25,000 feet. Their aircraft direction finders helped pilots navigate across featureless oceans, but powered turret design represented entirely new territory. The company's initial engineering estimates suggested meeting the Army's specifications would require breakthroughs in hydraulic system design that might take years to achieve, if they were possible at all. Preston Tucker joined Sperry's turret development program in August 1940 as a consulting engineer. He was 36 years old, and his resume looked distinctly unconventional for someone about to revolutionize military hardware. He'd grown up in Ypsilanti, Michigan, where his father ran a small machine shop. He'd attended Purdue University for 2 years, studying mechanical engineering, before the Depression forced him to drop out and find work. He spent the 1930s designing industrial hydraulic systems for automotive plants in Detroit, work that gave him extensive hands-on experience with high-pressure fluid power but little theoretical foundation in advanced mathematics or formal engineering analysis. Sperry's chief engineer, Carl Norden, hired Tucker based on a recommendation from an automotive industry contact. Norden needed someone who understood hydraulic systems from a practical perspective, someone who could build prototypes quickly and iterate through designs without getting bogged down in theoretical analysis. Tucker's first day at Sperry's plant in Lake Success, he walked into a paritaker conference room where the turret development team had assembled to brief him on the project's status. The news wasn't encouraging. Lead engineer Robert Sinclair explained the problem using a blackboard covered in equations. To achieve the rotation speeds required by Army specifications, the hydraulic system needed to deliver high flow rates to the turret motors. High flow rates required either large diameter hydraulic lines, which violated weight restrictions, or high fluid velocities through smaller lines, which created turbulence and control problems. Turbulence in the hydraulic fluid caused pressure fluctuations. Pressure fluctuations translated directly into jerky, imprecise turret movement that made accurate gunnery impossible. British systems solved this problem by using large diameter lines and accepting the weight penalty. American specifications didn't allow that approach. Sinclair's calculations suggested that any hydraulic system light enough to meet weight requirements would be too turbulent to provide the smooth control necessary for accurate fire. The two requirements appeared mutually exclusive. Tucker asked how fast the system needed to respond. Sinclair consulted his notes. Army specifications called for the turret to accelerate from rest to maximum rotation speed in under half a second and decelerate back to rest in similar time. Full rotation speed must be at least 30 degrees per second, allowing the turret to traverse its full 360-degree arc in 12 seconds. Tucker did some quick arithmetic on the margin of Sinclair's notes. 30 degrees per second meant covering a 90-degree quadrant in 3 seconds. That would allow a gunner to track a fighter crossing from beam to beam, but just barely. He asked what fluid Sinclair planned to use. "Standard aircraft hydraulic fluid," Sinclair replied. "Petroleum-based, operating pressure around 1,500 pounds per square inch, similar to what powered landing gear and flight control systems on existing aircraft." Tucker looked at the equations covering the blackboard and asked a question that would change the direction of the entire program. "What if we're using the wrong fluid?" The room went quiet. Sinclair asked what he meant. Tucker explained that petroleum-based hydraulic fluids worked well for systems that operated occasionally, like landing gear that extended once per flight and retracted once per landing. But a turret system would operate continuously during combat, with the hydraulic pump running, fluid circulating, and control valves cycling hundreds of times per mission. Continuous operation generated heat. Petroleum fluids became thinner as they heated up, changing their viscosity and therefore their flow characteristics. Viscosity changes meant pressure fluctuations. Pressure fluctuations meant control problems. But there was another class of hydraulic fluids that maintained consistent viscosity across wide temperature ranges. Synthetic fluids based on phosphate esters had been developed in the 1930s for specialized industrial applications. They cost significantly more than petroleum products, and nobody had ever used them in aircraft systems. But if consistent viscosity could reduce turbulence and improve control precision, the cost might be justified. Sinclair pointed out that synthetic fluids had never been tested at high altitude or extreme cold. They might freeze or break down in ways petroleum fluids didn't. Tucker suggested they find out. Within a week, Sperry had procured samples of several synthetic hydraulic fluids from chemical companies in New York and New Jersey. Tucker set up a test rig in the corner of the machine shop, consisting of a hydraulic pump, a small rotary motor similar to what would drive a turret, control valves, and a system of clear plastic tubing that allowed visual observation of fluid flow. The rig operated inside a large freezer borrowed from the building's cafeteria, allowing Tucker to test fluid behavior at temperatures down to 40 below zero. The results surprised even Tucker. At standard operating temperatures around 70 degrees Fahrenheit, synthetic fluids showed significantly less turbulence than petroleum products when pumped through small diameter tubing at high velocities. More importantly, when Tucker cooled the test rig down to 40 below zero and ran the pump, synthetic fluids maintained smooth flow characteristics, while petroleum fluids became thick and sluggish, creating pressure spikes that would have made precise turret control impossible. Viscosity tests confirmed what the flow observations suggested. Petroleum hydraulic fluid changed viscosity by a factor of 8 between 70 degrees and 40 below zero. The synthetic phosphate ester fluid Tucker was testing changed viscosity by less than a factor of 2 across the same temperature range. That difference translated directly into control precision. With petroleum fluid, the system that worked smoothly at sea level altitude would become sluggish and unresponsive at 30,000 feet, where cold temperatures thickened the fluid. With synthetic fluid, the system would behave almost identically at any altitude the bomber could reach. Tucker wrote up his findings in a brief report that focused on practical results rather than theoretical analysis. He included photographs of fluid flow through the clear tubing, showing the dramatic difference in turbulence patterns between petroleum and synthetic fluids. He calculated that using synthetic fluid would allow the system to meet Army weight specifications while maintaining control precision, something petroleum-based designs couldn't achieve. Norden read the report and immediately authorized Tucker to redesign the entire hydraulic system around synthetic fluids. But changing the working fluid solved only one problem. The bigger challenge involved the control system that would allow gunners to track targets smoothly, despite the violent motion of the bomber and the psychological stress of combat. Conventional hydraulic controls used mechanical linkages between the operator's input and the control valves that regulated fluid flow to the motors. The gunner moved a lever or wheel, the mechanical linkage transferred that motion to a valve, and the valve opened to send hydraulic fluid to the motor. This approach worked adequately for relatively slow applications like steering industrial equipment. But for tracking fast-moving aircraft, mechanical linkages introduced delays and dead zones that made precise control nearly impossible. Every joint in the linkage had some slack, every bearing had some friction. These imperfections accumulated, creating a system where small inputs from the gunner produced no output movement at all. Then sudden large inputs caused the turret to jump or surge unpredictably. British turrets addressed this problem with complex mechanical computing mechanisms that tried to predict target motion and provide lead angle assistance. These mechanisms worked moderately well but added weight and required extensive maintenance. Tucker proposed a completely different approach. Instead of mechanical linkages between the gunner's controls and the hydraulic valves, he would use an electrical follow-up system. The gunner's control handles would rotate small electrical generators called cell-sins. These generators produced electrical signals proportional to handle position. The signals fed to servo motors that positioned the hydraulic control valves. As the valves opened, hydraulic fluid flowed to the turret motors, rotating the turret. As the turret rotated, feedback cell-sins mounted on the turret rotation axis generated electrical signals indicating turret position. These feedback signals opposed the input signals from the gunner's controls. When the turret position matched the control handle position, the input and feedback signals cancelled. The servo motors returned the hydraulic valves to neutral and turret rotation stopped. The gunner experienced the sensation of directly controlling the turret position with his hands, but with no mechanical connection whatsoever. The beauty of Tucker's electrical follow-up system lay in its elimination of mechanical slack and friction. Electrical signals travelled at the speed of light. The servo motors positioning the hydraulic valves could be designed with minimal friction and no backlash. And, most importantly, the relationship between handle position and turret position could be made completely linear. A small handle movement produced a proportional small turret movement. A large movement produced a proportional large movement. The response felt natural and predictable, allowing gunners to track targets smoothly even under the stress of combat. But Tucker's system had one more critical innovation. Instead of trying to predict target motion with complex mechanical computers, he would let the turret's own motion provide the solution. The Sperry K3 and K4 computing gun sights being developed in parallel by another engineering team measured how fast the gunner was rotating the turret by monitoring the rotation rate of the turret's axis. The gun sight's analog computer used this rotation rate information, combined with range data input by the gunner and built-in ballistic tables, to calculate the required lead angle automatically. As the gunner tracked the target by keeping it centered in his sight, the computer automatically offset the sight reticule by the proper amount to compensate for bullet travel time, target motion, and the bomber's own movement. The genius of this integrated design meant the gunner didn't need to calculate anything. He simply kept the target centered in his sight. The turret rotation speed told the computer how fast the target was crossing his field of view. The range setting told the computer how far away the target was. The computer calculated the lead and moved reticule to show the gunner where to aim. And because Tucker's hydraulic control system responded smoothly and predictably to the gunner's inputs, the gunner could track precisely enough to keep the target centered while the computer did the mathematics. By December 1940, Tucker had built a full-scale prototype of the upper turret system. The turret dome sat on a test stand in Sperry's workshop, driven by the new hydraulic system and controlled through a mock-up of the gunner's station with control handles and a K3 gun sight. Engineers mounted a camera on a motorized track that could be programmed to simulate fighter attack patterns, giving the test gunner a moving target to track. The first test runs revealed problems Tucker hadn't anticipated. The synthetic hydraulic fluid performed exactly as expected, maintaining consistent viscosity and flow characteristics. The electrical follow-up system eliminated mechanical slack and provided smooth, responsive control. But under rapid slewing movements, when the gunner tried to swing the turret quickly from one target to another, the system became unstable. The turret would oscillate, overshooting the desired position, reversing direction, overshooting again, creating a hunting behavior that made precise aiming impossible. Tucker recognized the problem immediately from his experience with industrial hydraulic systems. The control system was too responsive. It reacted to input commands so quickly that by the time the gunner's brain registered that the turret had moved, the turret had already moved too far. The gunner would reverse his input to correct the overshoot, but the control system responded to that reversal so quickly that it created an overshoot in the opposite direction. The result was oscillation that could only be stopped by the gunner releasing the controls entirely and letting the system settle. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The solution required adding what control engineers called damping to the system. Tucker needed to slow down the system's response just enough to prevent oscillation while maintaining fast enough response to track crossing targets. He experimented with several approaches. Adding mechanical friction to the control handles helped, but introduced dead zones where small inputs produced no output. Installing hydraulic dampers in the turret drive system worked better, but required additional components that violated weight restrictions. The answer Tucker finally settled on was elegant in its simplicity. He modified the electrical follow-up circuits to include small capacitors that smoothed out rapid changes in the control signals. These capacitors acted like electrical shock absorbers, allowing steady inputs from the gunner to pass through unchanged but filtering out the rapid oscillations that caused instability. A gunner making a smooth tracking motion experienced no change in system behavior, but rapid jerky movements were automatically smoothed by the capacitor filtering, preventing oscillation while still allowing the fast response needed for combat. By February 1941, the upper turret system worked reliably enough for Army acceptance testing. A test installation in a B-17E airframe at Wright Field demonstrated that the turret could traverse its full 360-degree arc in under 12 seconds, accelerate to maximum speed in half a second, track smooth curves with no oscillation, and maintain precise control down to temperature of 50 below zero at simulated altitudes of 35,000 feet. The ball turret presented even more severe challenges. The entire turret assembly, including the gunner, two 50 caliber machine guns, ammunition cans holding 500 rounds, and all control systems had to fit inside a sphere just 44 inches in diameter. This sphere would hang beneath the bomber's fuselage, suspended from a ring gear that allowed rotation in azimuth, while trunnions permitted elevation from 22 degrees above, horizontal to 90 degrees straight down. Every cubic inch inside that sphere was precious. There was barely room for the gunner himself, who had to assume a cramped fetal position with his knees drawn up, his back against the rear wall, and his feet in stirrups that positioned them on either side of the optical sight. The guns occupied the forward hemisphere. Ammunition cans filled the spaces beside the gunner's hips. The hydraulic pump and motors had to fit somewhere in the remaining space, along with the electrical wiring, control mechanisms, and the Sperry K4 computing site. Tucker's team spent months working out the packaging. Every component was redesigned multiple times to save weight and space. The hydraulic pump became a compact unit that mounted directly on the elevation trunnion, where it could be driven by an electric motor positioned outside the ball's pressure hull. The azimuth drive motor nested inside the ring gear assembly. The elevation motor mounted on one of the trunnions. Hydraulic lines were routed through the narrowest possible passages, with fittings specially designed to minimize bulk. The control handles that the gunner used to position the turret were positioned at waist level on either side of the gunner's seat. Pushing forward on both handles pitched the turret downward. Pulling back pitched it up. Moving the handles in opposite directions rotated the ball in azimuth. The gunner could combine these motions to track targets moving in any direction through the lower hemisphere. The K4 sight hung from the ceiling of the ball directly in front of the gunner's face. Looking through the sight, the gunner peered through a circular optical glass window between his feet, giving him a clear view of the area below and around the bomber. The computing system used the turret's motion to calculate deflection exactly as in the upper turret system. As long as the gunner kept the target centered in the sight's reticules, the computer automatically provided the proper lead angle. But the ball turret's cramped space created a psychological challenge that Tucker's engineering couldn't solve. Gunners entering the ball for the first time experienced claustrophobia, vertigo, or both. They sat in a metal sphere suspended beneath a bomber flying at 30,000 feet, looking straight down through their feet at Earth 6 miles below, while the entire sphere rotated and tilted around them in response to their control inputs. Some men adapted quickly, others never adjusted. The Army's solution was to select ball turret gunners primarily based on stature. Men, 5'6" or shorter, who could fit comfortably in the cramped space, were tested for psychological resilience. Those who could handle the vertigo and confinement became ball turret gunners. The rest were assigned to other crew positions. But for the men who could master the ball turret, Tucker's hydraulic system gave them the most capable defensive position on the aircraft. The turret could track targets through 360 degrees of azimuth and nearly 90 degrees of elevation. Rotation speeds of 30 degrees per second in both axes allowed the gunner to swing rapidly from target to target, and the smooth, precise control provided by Tucker's system meant an experienced gunner could maintain accurate tracking through complex maneuvering by both the bomber and the target. First combat tests of the Sperry turret system came in summer 1942, when B-17Es began arriving in England for operations with the 8th Air Force. The B-17E was the first model to incorporate powered turrets as standard equipment. A Sperry upper turret sat directly behind the cockpit, operated by the flight engineer. A Sperry ball turret protected the ventral area. Manually operated 50 caliber machine guns in the waist, radio room, and nose positions provided additional coverage. Early missions against targets in occupied France revealed both the strengths and limitations of the turret systems. German fighters, still flying older Messerschmitt 109F models and Focke-Wulf 190A models, approached at speeds around 300 miles per hour. Turret gunners found they could track these targets smoothly, using Tucker's hydraulic control system. The electrical follow-up system responded precisely to control inputs. The K3 and K4 computing sites calculated lead angles automatically, and when gunners squeezed the firing buttons on their control handles, the twin 50 caliber Brownings hammered out rounds that often found their targets. But hit probability remained frustratingly low. Post-mission analysis of gun camera footage and ammunition expenditure showed that even experienced gunners achieved only about 2% hit rate against maneuvering targets. This meant a gunner needed to fire 50 rounds to score 1 hit. With the typical ball turret ammunition load of 500 rounds total across both guns, that allowed for just 10 hits during an entire mission if ammunition was expended continuously. In reality, actual combat firing occurred in short bursts lasting a few seconds each, and most missions saw gunners engaging targets multiple times, so actual hits per mission averaged considerably lower than 10. The problem wasn't the turret system or the guns, it was the inherent difficulty of deflection, shooting at high speeds. A fighter crossing at 400 miles per hour from the beam at 600 yards range required a lead angle of approximately 15 to 20 degrees, meaning the gunner had to aim a distance of over 200 feet ahead of the target to compensate for bullet travel time. The computing site calculated this lead automatically and displayed it through the reticule offset, but the gunner still had to maintain perfectly smooth tracking to keep the target in the sight picture while the computing system did its work. Any unsteadiness in tracking, any over-control or oscillation, translated into missed shots. Tucker's hydraulic system gave gunners the smooth, responsive control they needed, but it couldn't eliminate the fundamental challenge of hitting small, fast-moving targets at ranges where bullet travel time exceeded 1 second. What the system could do, and did remarkably well, was allow gunners to maintain sustained fire on targets throughout their attack runs. Even if most rounds missed, the psychological effect on German fighter pilots of flying through streams of 50 caliber tracer fire proved substantial. Luftwaffe after-action reports from 1942 and 1943 missions frequently mentioned the intimidation factor of American defensive fire. German pilots described walls of tracers converging from multiple bombers simultaneously as they pressed attacks. Many pilots broke off attacks earlier than optimal to avoid the defensive barrage, reducing their own effectiveness even when American gunners failed to achieve hits. By late 1943, When improved models like the B-17G entered service with 13 defensive gun positions, including a powered chin turret in the nose, the volume of defensive fire from a combat box formation became truly formidable. A group box of 27 B-17Gs carried over 300 heavy machine guns, providing interlocking defensive coverage. German fighters attempting to penetrate such formations faced the prospect of being tracked by dozens of turrets simultaneously, all using Tucker's hydraulic system to maintain smooth aim. Statistics bore out the effectiveness of this mass firepower approach. Loss rates for B-17 formations over Germany in 1944 averaged around 3 to 4% per mission, down from 6 to 8% in 1943. While much of this improvement came from the introduction of long-range fighter escorts, the enhanced defensive firepower provided by reliable powered turrets contributed significantly. German fighters that had previously pressed attacks aggressively against early B-17 models with limited defensive armament became notably more cautious when facing formations of G models with comprehensive turret coverage. The Sperry turret system proved remarkably reliable in service. Failure rates ran below 1%, meaning that in a typical 100-bomber raid, fewer than one turret would fail due to mechanical problems. This reliability reflected the soundness of Tucker's fundamental design decisions. Synthetic hydraulic fluid maintained consistent performance across all operating conditions. The electrical follow-up system had no mechanical parts to wear or break. The hydraulic motors and pumps used simple, robust designs that rarely failed. Maintenance proved straightforward. Ground crews serviced the hydraulic systems between missions, checking fluid levels, inspecting lines for leaks, and testing control response. The synthetic fluid required changing less frequently than petroleum-based products because it resisted thermal breakdown even under the continuous operation cycles common during long missions over Germany. Electrical components occasionally failed, particularly Celsin generators and servo motors that were exposed to temperature extremes and vibration, but these failures typically produced obvious symptoms that maintenance crews could diagnose and repair quickly. The computing sites required more specialized maintenance, but Sperry's design included built-in test systems that allowed technicians to verify site accuracy without requiring flight testing. The most common problem gunners reported involved physical discomfort rather than equipment failure. Operating a powered turret required sustained concentration and physical exertion. The gunner's hands gripped control handles continuously, making small, precise movements to track targets. His eyes strained to spot fighters at maximum range, often against bright cloud backgrounds or directly into the sun. The temperature at 30,000 feet typically ran 40 below zero, cold enough to cause frostbite, despite heated flying suits, and the oxygen masks required at high altitude became uncomfortable during missions lasting 8 to 10 hours. Ball turret gunners faced additional challenges unique to their position. The cramped space made it impossible to shift position during the mission. The gunner couldn't stand, stretch, or move around. He remained curled in his fetal position for the entire mission duration, entering the turret shortly after takeoff and exiting only after landing. The psychological demands of sitting suspended beneath the aircraft, looking down at Earth 6 miles below, while German fighters attacked and anti-aircraft shells burst around the formation tested even the most resilient men. Yet, for all these difficulties, ball turret gunners achieved some of the highest kill claims in the 8th Air Force. The combination of excellent visibility from their position, 360-degree coverage, and the smooth tracking provided by Tucker's hydraulic system made them particularly effective against fighters attacking from below or making beam passes. Post-war analysis credited ball turret gunners with approximately 15% of all confirmed German fighter kills by bomber defensive gunners, a remarkable figure considering they represented only about 10% of the gunner positions on B-17 seconds. Tucker left Sperry in early 1944 to pursue other projects. His work on the B-17 turret system earned him a certificate of commendation from the Army Air Forces and a modest bonus from Sperry, but no public recognition. The engineering challenges he'd solved, the innovations he'd introduced, remained classified throughout the war. He'd proven that synthetic hydraulic fluids could work in aircraft systems, opening the door for their adoption in post-war jet aircraft, where reliable high-performance hydraulics became essential for flight control. He demonstrated that electrical follow-up systems could provide precise control of hydraulic actuators, a principle that would be applied to everything from industrial robots to spacecraft control systems, and he'd shown that properly designed human-machine interfaces could allow operators to perform complex tasks under extreme stress, lessons that informed decades of subsequent aerospace human factors engineering. The Sperry turrets remained in service through the end of World War II. Over 12,000 B-17 seconds were equipped with Tucker's hydraulic system. Conservative estimates suggest the turrets contributed to shooting down or driving off several thousand German fighter attacks that might otherwise have destroyed bombers and killed their crews. The synthetic hydraulic fluid Tucker specified became standard for American military aircraft in the post-war era, chosen for its consistent performance across temperature extremes. And the electrical follow-up control architecture he pioneered influenced hydraulic system design in applications ranging from earth-moving equipment to aircraft flight controls for decades after the war. Preston Tucker went on to attempt building an automobile bearing his name in the late 1940s. The Tucker 48 featured numerous innovations, including a rear-mounted engine and advanced safety features, but production problems and financial scandals destroyed the company before it could establish itself. Only 51 Tucker automobiles were built. The automotive venture's failure overshadowed Tucker's earlier engineering achievements, and today he's remembered primarily for the car that didn't succeed rather than the turret system that helped win the air war over Europe. But on that November afternoon in 1943, when Staff Sergeant Callahan swung his ball turret through a 90-degree arc in under 2 seconds and put 50 caliber rounds into a Messerschmitt at a combined closure speed, exceeding 600 miles per hour, he was demonstrating the triumph of Tucker's engineering vision. The hydraulic fluid flowing through the system maintained perfect viscosity despite external temperatures of 40 below zero. The electrical follow-up circuit responded to Callahan's control inputs with precision measured in milliseconds. The computing site calculated lead angles using the turret's own rotation speed as input, providing aiming solutions that would have required extensive calculation if done manually. The entire system, weighing under 600 pounds, operated reliably at altitudes where humans needed supplemental oxygen to stay conscious. It wasn't the advanced engineering degree that made Tucker's system work. It was his understanding that aircraft systems needed to function in environments far more hostile than the laboratories where they were designed. His willingness to challenge conventional wisdom about hydraulic fluids and control systems. His recognition that elegant solutions often came from simplification rather than complexity, and his insight that helping gunners track targets smoothly mattered more than trying to predict target motion through elaborate computing mechanisms. The Messerschmitt that Callahan shot down was the second of his tour, which would eventually total 6 confirmed kills before his 25th mission over Germany. He would return to his home in Philadelphia in July 1944, train new ball turret gunners at Flexible Gunnery School in Kingman, Arizona, and fly B-29 missions over Japan in 1945. After the war, he opened a sporting goods store and lived until 1997, long enough to see his B-17 ball turret restored and displayed at the National Air and Space Museum in Washington, where visitors could look at the cramped space and marvel that anyone could fight from such a position. The turret system he used that day in November 1943, the system that let him swing smoothly onto target and squeeze off the burst that sent the Messerschmitt down, continued operating on display aircraft for decades after the war. Restorers who serviced these systems frequently commented on their remarkable reliability. Add hydraulic fluid, apply electrical power, and turrets built in 1943 would rotate smoothly, track precisely, and respond to control inputs as though they'd been manufactured the previous year. That was Tucker's legacy. Not the car that failed, but the unglamorous hydraulic system that worked exactly as it needed to, when it needed to, under conditions that would have broken less carefully thought-out designs. 26,000 feet below Callahan's turret, the Messerschmitt he'd just hit continued its descent, trailing smoke. The pilot had already bailed out. That meant one fewer fighter to attack the next bomber formation, one fewer gun firing at American aircraft, one mission closer to the end of the war. Tucker's hydraulic system didn't end the war. No single technology ever does. But it gave American airmen the tools they needed to defend themselves against one of the most aggressive and skilled fighter forces in aviation history, and it did so reliably. Mission after mission, across 3 years of the most intense aerial combat the world had ever seen. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.